Hello everyone, this video is the fifth in my series explaining AIME problems. In this video, I'll be talking about counting problems and the ways that they can be solved. I encourage you to pause throughout the video and try to solve the problems. Here are some general tips for counting problems. You should find ways to make the problem easier than it looks. You should break up casework problems into cases that are not too big or too specific. You should find ways to make problems similar to the problems you know, because then they're easier to solve. Finding the opposite of what you want can sometimes help. And visualizing the problem sometimes helps. And it's always possible to change a method of doing a problem if you're stuck. Let's start with a simple casework problem. Let the set S equal 8, 5, 1, 13, 34, 3, 2, 21, 2. Susan makes a list as follows. For each two-element subset of S, she writes on her list the greater of the set's two elements. Find the sum of the numbers on the list. Let's start by trying to make the problem a bit easier. First, let's order this set. We get it is equal to the set 1, 2, 3, 5, 8, 13, 21, and 34. Now, let's find the number of times each number comes up. 1 just comes up 0 times since it's greater than none of the elements. 2 comes up 1 time since it's greater than 1. 3 comes up 2 times since it's greater than 2 and 1. 5 comes up 3 times since it's greater than 3, 2, and 1. And this continues all the way to 34, coming up 7 times. So we can just multiply each number by the number of times it comes up, which is 34 times 7 plus 21 times 6 plus 13 times 5, all the way to plus 2 times 1 plus 1 times 0, which equals 484, which is our answer. Here's another casework problem. At a certain university, the Division of Mathematical Sciences consists of the departments of Mathematics, Statistics, and Computer Science. There are 2 male and 2 female professors in each department. A committee of 6 professors is to contain 3 men and 3 women, and must also contain 2 professors from each of the 3 departments. Find the number of possible committees that can be formed subject to these requirements. Let's start by trying to visualize some of these cases. Each department, let's call them M, S, and C, have 2 male and 2 female candidates, or professors. And we need to choose 2 candidates from each category such that there are total 3 male and 3 female. There's only 2 ways in which we can do that, which is MM from one, FF from another, and then MF from the third. Or we can just do MF from all 3. For the first case, there's exactly 3 factorial ways to order who gets MM, FF, and MF. And then for MF, there's 2 times 2 ways to choose the males and females. And for MM and FF, there's only 1 way to choose, which gives a total of 24 ways for this case. For the second case, there's 2 times 2 cubed ways, since for each group, there's 4 total ways. And this gives a total of 64. So our answer is 88. Let's now explore a problem in which there is a correspondence. Find the number of ordered pairs of positive integers a, b, such that a plus b equals 1000, and neither a or b has a 0 digit. Nothing pops out immediately, but we can rewrite this problem. A plus b equals 1000 can be written as CDE plus FGH equals 1000, CDE plus FG equals 1000, or CDE plus H equals 1000, where all of the letters are digits. Now, we know that E and H have to equal 10. the sum has to equal 10. D and G have to equal 9. The sum of D and G has to equal 9 because the 1 will carry over. And C and F, the sum, also has to equal 9 for the same reason. E and G here have to equal 10. D and F have to equal 9. And C has to equal 9. And here, E and H have to equal 10. D has to equal 9. And C has to equal 9. So, for this, there's exactly 9 times 8 times 8 ways of solving this problem, which gives a total of 576 ways. For this case, there's exactly 9 times 8 ways, which gives 72. But we have to multiply this by 2 since it's ordered pairs of positive integers. So we get 144. And for this, there's exactly 9 ways, and we multiply it by 2 again to get 18. So the sum, which is our answer, is 576 plus 144 plus 18, which is 738. Let's now look at a problem that involves complementary counting, or counting the opposite. Let Si be the set of all integers n, 100i is less than or equal to n is less than 100i plus 1. For example, S4 is the set 400, 401, 402, 403, continued, 499. How many of the sets S0, S1, S2, S3, continued, S999 do not contain a perfect square? Let's rephrase this question first. How many of the sets do? And this may make it easier, because whichever sets after the ones which are less than 100 apart do have to contain a perfect square. We can draw a correspondence with those number of sets and the number of perfect squares. So first let's find the number of squares that are less than 100 apart. So n plus 1 squared is less than n squared plus 100, in which we get n is less than or equal to 49. So we at least have that till 50 squared, all the sets under it contain a perfect square. And this is 2500. So we know that from S0 to S25, they contain a perfect square. Now, what is the largest square under 99999? This turns out, after some calculation, to be 316. And that means that from 51 to 316, these have a correspondence with the number of sets that contain a perfect square. And the numbers here are 266. So adding that with 26, we get that this equals 292. So to get our final answer, we have to subtract it from the total number of sets, which is 1000. And this gives us that our answer is 708. Let's move on to another problem. This problem looks pretty long, so we have to make sure to read through it carefully and understand every bit. There's an unlimited supply of congruent equilateral triangles made of colored paper. Each triangle is a solid color with the same color on both sides of the paper. A large equilateral triangle is constructed from 4 of these paper triangles. 2 large triangles are considered distinguishable if it is not possible to place one on the other using translations, rotations, and/or reflections so that their corresponding small triangles are of the same color. Given that there are 6 different colors of triangles from which to choose, how many distinguishable large equilateral triangles may be formed? So this is the diagram of a large equilateral triangle constructed from 4 small triangles. Now, let's try to visualize the cases. For the middle, there will be 6 ways of choosing the value, since you can't rotate it onto itself. So I'll put a 6 there. Now, let's say we choose 3 different colors. Then we get, for example, A, B, and C. This is the same if we reflect it as A, B, and C this way, which is also the same as A, B, and C. So we come to a finding that for 3 different colors, there's only one way of arranging it. And since there's exactly 6 choose 3 ways of getting 3 different colors, we get that the total number of arrangements for this case is 20. For 2 different colors, so this is 1 and 2, this becomes A, and B. And this can also be rotated or reflected as this, or this, which are all the same. So we get that there's also only one way of arranging 2 different colors, but there are exactly 30 ways of getting 2 different colors, since there's 6 for the one that's getting 2 twice, and 5 times for the 1. And if they're all the same color, there's only one way of arranging it, and there's 6 ways of choosing the color. Now, we have to add up all these values and multiply by 6, since the middle can be any color. So we get that this equals 56 times 6, or the answer is 336. Let's end with the problem that demonstrates the importance of looking at the cases. Find the positive integers n less than 1000 for which there exists a positive real number x, such that n equals x times the floor of x. Note, the floor of x is the greatest integer less than or equal to x. So let's start this for 0 to 1. But x cannot be 0 or 1 right now. So then this just gives 0 to 0, 0 times 0, or 0 times 1, but none of these work, so this is not possible. Now let's try it from 1 to 2, but not equal to 2. This gives 1 times 1, 2, 1 times 2. Because once it hits 2, it jumps, as we'll see soon. So this just gives 1 to 2, but not equal to 2, and so there's one possible case. Then from 2 to 3, but not equal to 3, we get 2 times 2 to 2 times 3, or 4 to 6, but not equal to 6. So there's 2 cases. And similarly, from 3 to 4, but not equal to 4, we get 3 cases. So we see a pattern here that for every integer x, there's exactly that many n that are possible. So let's try to prove it. From an integer x, let's say x, then to get to x plus 1, we need to do x squared all the way to x times x plus 1, but not equal to x times x plus 1. This gives x squared plus x minus x squared n. And this is just xn. So all we have to do is find the largest integer x for which this is possible. And we get that the largest integer x that works is 31, because 31 squared to just under 32 squared is 961 to 992, which is still under 1000. So our final answer is 31 times 32 over 2, which equals 496. Thank you for listening. Please like and subscribe, and remember to click the bell icon for more updates.